Okay, so now we're going to compare and contrast an algebra with a topology so that we can better understand what a topology is and make more sense of all these new terms. So let X be any set. An algebra over the set X is a collection F of subsets of the set X that is closed under arbitrary unions arbitrary intersections and complements of all subsets in the collection F. Now, what do we mean by closed under these operations? Any union of elements in the collection F is once again in the collection F. Any intersection of the elements in the collection F is once again in the collection F. And the complement of any subset in the collection F is once again in the collection F. Now, the collection F, consisting of the empty set and the entire set, is the smallest collection of subsets of the set X that constitutes an algebra over the set X. And as you might guess, this is called the trivial algebra. Over the set X. Now, in contrast, a topology over the set X is a collection tau of subsets of X which is closed under arbitrary unions finite intersections and complements of what we call closed sets. And by this we mean it's closed under the double complement of the subsets in the collection tau. So the complement of a set in the collection tau is called a closed set because the topology is closed under the complement of those sets. Okay, as we know, the topology tau consisting of the empty set and the entire set is the trivial topology. This is the smallest collection of subsets of the set X that is a topology. So notice that not every topology is an algebra, but every algebra is a topology. However, in the topology F, every subset in the collection F is both open and closed. And in general, this is a very undesirable condition because, as we will see, this leads to or results in a disconnected space. Some mathematicians and the corresponding literature refer to a set that is both open and closed as a clopen set. After now, you will never hear me utter that term again. I'm not a fan of that term at all. Now, by only requiring that finite intersections and complements of closed sets be closed operations over the collection tau, this gives an orientation to the space, as we will see. And in this way, topology is much more like geometry than algebra. In fact, topology is a different way of thinking about the geometry of the underlying space. So recall that the boundary of a set, subset A, is by definition the complement of the union of the interior of that set with the exterior of the set. The boundary is a closed set since its complement is the open set, which is the union of two open sets where the interior of the set A is the largest subset of the set A that is open. The exterior of the set A is the subset of the complement of the set A that is open. The closure of the set A is the smallest superset of the set A that is closed, which once again means that its complement is in the topology. Now, before we start to look at some examples, we're going to prove a theorem that gives us a different way to compute the boundary, and this will also give us another interpretation of the boundary. So let X together with some topology tau be a topological space. And let A be a subset of the space X. Then the boundary of A is the closure of A set minus the interior of A. That is the complement of the interior of A in the closure of A. So proof. Once again, by definition, the boundary of A is the complement of the union of the interior of A with the exterior of A. The complement of a union is the intersection of complements, and so this is the intersection of the complement of the interior of A with the complement of the exterior of A. The exterior of A is the complement of the closure, and so this is the complement of the closure. And so we have the intersection of the complement of the interior of A with the closure of A. Now, since the interior of the set A is a subset of the closure of the set A, which is itself a subset of the entire space. The closure of A intersected with the complement of the interior of A in the entire space is the complement of the interior of A in the closure of A. And so the boundary of A is the closure of A set minus the interior of A. So now we have a different way to compute the boundary, which is a little easier in most cases. But this also gives us a new interpretation. The boundary is that portion of the closure of A that completely contains the subset of A that is in the topology. So now we can look at some examples. Let tau sub I be the set containing the empty set and the set of reals. That is, we have the indiscrete or trivial topology on the set of reals. Let's consider the subset of the real line. Oops. I hesitate to call this the real line because to use the term the real line implies the standard topology, and here we're using the indiscrete topology. The subset of the set of reals, which in interval notation is this, where this interval is the set of all those real numbers that are strictly greater than A and strictly less than B. Now clearly, this subset is not in the topology and is therefore not open. So we cannot refer to this as the open interval in the space on the reals consisting of this topology. Let's now look at the complement. The complement of this set is the set which contains all those real numbers less than or equal to A, which in interval notation we can note it this way, and all those real numbers that are either greater than or equal to B, which in interval notation is this. And also this set is not in the topology, and so the interval from A to B is not closed since its complement is not open. And so the interval from A to B is neither open nor closed in the space consisting of the set of reals with the indiscrete or trivial topology. So now that we know that this set is neither open nor closed, we need to compute its interior and closure. The only open set contained in the interval is the empty set. And so the interior of the interval is the empty set. Now, if we give a geometric interpretation of this statement, what we mean is that the subset, which is the interval from A to B, does not have an interior in the space consisting of the set of reals with this topology. Now, the only closed set containing this interval is the entire set of reals. And so the closure of the interval is the entire set of reals. So now that we know the interior and closure, we can calculate the boundary. The boundary of the interval is the closure of the interval, set minus the interior of the interval. And this is the entire set of reals, set minus the empty set, which is the entire set of reals. So again, as a geometric interpretation, that portion of the closure of the interval that contains, completely encloses the portion of, or the subset of, the interval that is open is the entire real line. Or, correction, the entire set of reals. So now the exterior of the interval is the complement of the closure of the interval. So this is the complement of the entire set of reals in itself, which is the empty set. So geometric interpretation of this statement is that the set, the interval from A to B, has no exterior in this space. And one more calculation, we'll calculate the complement of the boundary, which is the union of the exterior and interior. This is the complement of the real set of reals in itself, which is empty. So let's look at the geometry of this subset in this space. The subset, once again, is the interval, that is all real numbers, strictly greater than A, strictly less than B. This subset has no interior. The interior is empty. The closure of the set is the entire set of reals. The boundary of this set is the entire set of reals. The exterior is empty. And the complement of the boundary, which once again is the union of the interior and exterior, is also empty. There is no exterior, there is no interior for this set in the space consisting of the reals with the indiscrete or trivial topology. And this should not surprise us, as this topology has only two open sets, the empty set and the entire set, where these sets are both open and closed. And so every closed set is going to be either the entire set or the empty set. And likewise, every open set is going to be either the empty set or the entire set. All right? Now, this is not a unique condition for this particular interval. Once again, let T sub I be the indiscrete or trivial topology on the set of reals. And let the set A be a proper subset of the set of reals that is non-empty. So a non-empty proper subset. The only open set contained in this set is the empty set, and so the interior of the set A is the empty set. The closure of A is the entire real line, or correction, the entire set of reals, because this is the only closed set that contains the set A. And so the boundary of A is R set minus the empty set, which is the entire set of reals. The exterior of the set A is the complement of the closure. Closure of A, which once again is the complement of the reals in itself, which is the empty set. And so we can also look at the sets that are in the topology for the empty set. The empty set is both open and closed, and so it is its own interior and its own closure. The boundary of the empty set is the closure set minus the interior, which is empty. And the exterior of the set is the complement of the closure, which is the entire set of reals. Now for the reals, we have that it is its own interior as it is open. It is also its own closure since it is closed. The boundary of the entire set is the empty set. And the exterior of the entire set of reals is the empty set.